So last week when we were talking about probability, we looked at these 4 general rules. And I need to get this up here. Sorry, one second. Okay, sorry about that. Okay, we looked at these 4 general rules, which the 3 of them, okay, rules 1, 2, and 4, are all based off of that idea that everything in the sample space needs to add up to 1. That 3rd rule was looking at when the events are disjoint, meaning that they do not overlap each other. They cannot occur simultaneously. Now, for that, we said the key word was or means add, and you can just simply add probability of A plus probability of B, gives you that probability of A or B. But it really wasn't that much of an accommodation to make if the 2 did overlap. And this is if they're disjoint or mutually exclusive. But here, if they're not disjoint, that means that they just have a little bit of overlap, and to make that change, we can just subtract away that probability that both of them happen. Because we don't want it to be counted twice. So probability of A plus B minus this region that's been counted both times leaves us with probability of A or B. Okay, so there's this idea that even though we're following rules, if it doesn't fit that rule to a T, that's not the end of the world. We can make adaptations to think about, well, what's really going on here? Why does this go against the rule? And we can make that fix to move forward and make progress. We're going to see that a little bit more today, where we started to talk about independence. We did the couple practice problems there. We started then to talk about this multiplication rule, where this is the fundamental idea for independence. If 2 events are independent of each other, then with our verbal definition, the outcome of one has no impact or influence on the outcome of another. Now, we said there's this verbal definition that people like to look at. However, a more complete understanding is based off of this equation. And in order to prove independence, we need to show that it satisfies this equation. Okay, we get to this key idea that for multiplication, we're using the word and. Previously, with addition, we were using the word or. Or means add, and means multiply. Now, what can be a little bit of a challenge here is that sometimes we don't always express the word and. You'll see this in some of the problems that we're looking at today. I know one we're talking about like a cookie problem, where there's a bunch of cookies in a jar. Some of them are made, some of them are chocolate cookies, and they're made by a generic company, okay, as opposed to a name brand company. So if you're describing that cookie, you're not always going to say it's chocolate and generic. Sometimes you'll just see it's a generic chocolate cookie. The and is implied. So that's one of the things that can make it a little bit more complicated. But just like we saw with disjoint events, we had this rule for independence. What if they are dependent? What if the outcome is based off of A, but that A value, that A probability, depends on what B is, or vice versa? That's what we're going to be looking at today when we talk about conditional probability. Usually when we have independent events, the opposite of that, we don't always say dependent events. Instead, we'll usually say they are not independent, or there's a conditional probability. Okay, that's the more common phrasing. So you can kind of read through here, but essentially what conditional probability does is it's changing the probability based off of more current information. Given the end, when we are trying to find the probability one event will happen, given that the information the other event is already known to have occurred, we are trying to determine a conditional probability. Now, our equation for this is denoted as such. Probability of B given that A has occurred. This vertical bar means given whatever is following has occurred. So this is equal to the probability of A and B divided by the probability of that condition. Now, I've already had a phrase that I've been using a lot with probability. I've been saying probability is meant for the long haul. It's meant for the big picture. That is true. But with conditional probability, there's one more phrase that's even more important. Conditional probability changes the sample space. Conditional probability changes the sample space. You'll see this is true a couple times over. Right? With this equation that we have in front of us, probability of B, given that A has occurred. Up top in the numerator, we're looking at the probability of A and B occurring together. Down in the denominator, the sample space, that's just the probability of A, the condition. If we were to switch this, and we wanted the probability of A given that B has occurred, that is not necessarily true to B given A has occurred. In fact, they're probably not going to be the same thing. But the only change to this equation, okay, you're still going to have probability of A and B up top. The only thing that's different is now the probability of the condition. B is downstairs in the denominator. And that is the new sample space. Only thing that's different when they're varied like this is that denominator, the sample space. Let's try some practice. Revisiting a problem we saw last week. These senior boys in their class. Remember, class of 20 students, seniors and juniors in the class, boys and girls in the class. We are interested in the probability of selecting a boy given that we select a senior. Well, we have this chart in front of us. One way to look at this is just by using the chart. So this had been out of our overall 20 students in the class. But we don't want that as our sample space anymore. Given that we choose a senior, well, we're not picking from our 20 students in the class, we're picking from our 11 total seniors. Of those 11 seniors, a success in this case is a boy, we had 8 boys. 8 out of 11, there's that probability. If we reversed these conditions, now probability of selecting a senior, given that we select a boy, probability of the condition, given that we choose a boy, that's our new denominator. We're changing the sample space. So there were 12 boys in the class. Of those 12 boys, still the same 8 seniors. That has not changed. 8 out of 12, or we could reduce this to 2/3. And that's what we have right there. Now, I think you'll find today that many of these problems, using a chart is going to be easy. It's going to be pretty straightforward. But just like we saw last week, you still want to be familiar with the equation. Let's take a look at how this satisfies the equation here. In this problem, our first condition, probability of selecting a boy given that we choose a senior. Well, we have this worked out right here that following along with this equation, probability of A and B, both of these events happening at the same time would mean a boy and a senior, of which there were 8 in the 20 people in this class. So we're doing 8 out of 20 divided by the probability of just the condition, which in this first case was the probability of selecting a senior. Well, in this class of 20, there were 11 seniors. So the probability of selecting a senior was 11 out of 20. That's the probability of that condition. That's the denominator. So what's happening here is 8 over 20 divided by 11 over 20. Division by fractions is the same as multiplying by the reciprocal. So this is really like 8 over 20 times 20 over 11. 20 in the numerator, 20 in the denominator. Those divide out to 8. You're left with your 8 over 11, which is what we had up there. One of the reasons why I said it's not that important that we reduce our fractions is to help us with this. Another reason is when we're adding fractions as part of the mutually exclusive or non-mutually exclusive, it helps to have common denominators there. When you're doing a conditional probability like this, those two denominators should divide each other out. And you're left with just 8 over 11 in this case. When we reverse the conditions, probability of selecting a senior given that we select a boy, well, again, you're going to be so tired of me saying this. Conditional probability changes the sample space. Look what does not change. We had 8 over 20 in the numerator before. We have 8 over 20 in the numerator here. Probability of a senior boy, probability of a senior boy. Both of those happening simultaneously. That does not change. What does change is the sample space. Before, the condition was probability of a senior, 11 out of 20. Here, it's the probability of a boy. There were 12 boys out of the 20 students in the class, so 12 out of 20. So 8 divided by 20, divided by 12 out of 20, or as I said, multiplication by the reciprocal, gone. 8 over 12, which reduces to 2/3. Anybody have any questions here? It's particularly important, especially you guys at home, to ask if questions occur along the way. All right? It's easier to answer these things now than to say a week and a half from now, right before a test, well, I didn't quite understand what was going on slide 12 in the conditional probability lesson. Okay? Let's get it cleared up right now so we can build on top of things that make sense. Okay. Let's look at rolling a pair of dice. This is a very common type of probability problem. We've already looked at some like coin flip problems. Rolling 2 dice, classic textbook example. I mentioned that I have this sample space as a document on Canvas where it's nothing but a page of like 9 of these sample spaces. Whenever you have a problem like this, I try to paste it in there for you to use because we're going to find that it's easy to kind of highlight this and make sense of it. Just like I mentioned last week, Make sure you either have the PDF of this up and you're annotating it, or you have some paper off to the side. Okay? I want you to be working these things out. You guys in class today, if you want to borrow or grab a piece of paper right there, you're welcome to do that. With this, remember we're rolling a pair of fair dice, meaning 6 outcomes on each die. 1, 2, 3, 4, 5, 6. Every outcome is equally likely. First die is this along the left side, second die is going across the top. So, our first outcome that we have denoted says the probability that at least one of the dice is a 4. That's what we're interested in. Probability at least one of the dice is a 4. Alright, so that would mean for this first die, I'd have a 4 and a 1, a 4 and a 2, a 4 and a 3, 4 and a 4, 4 and a 5, 4 and a 6. This entire row is a success. Any of these pairs are made when this first die is a 4. Additionally, it's also a success if this second die is a 4. So this entire column, 1 and a 4, 2 and a 4, 3 and a 4, I've already highlighted 4 and a 4. I don't want to do that again. 5 and a 4, 6 and a 4. So, one way to answer this question, probability at least one of the dice is a 4. I could count up our successes, our highlighted blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of our sample space of 36. Remember, multiplication principle, 6 outcomes times 6 outcomes, 36 total possible outcomes. Or we could go back to the equation. For our first die, we had 6 ways of a successful outcome, 6 out of 36. For our second die, 6 ways to roll a 4 on that die, so 6 out of 36. But we've counted this 4 and 4, a sum of 8, twice. So we've got to subtract away that overlap because these are not disjoint. 6 plus 6 is 12, minus 1, 11 out of 36. Same answer. Any questions so far? All right. For our next outcome, we are interested in the probability that the sum is 7. Well, on our chart here, the sums fall along these diagonals. So a sum of 7, 1, 2, 3, 4, 5, 6 different ways that could happen. 6 different ways that could happen. So, probability, 6 out of 36, or 1/6. This is a case where it's okay if we simplify the fraction. Back up here, this was an example as to why we did not want to simplify the fraction, because we were adding and we needed that common denominator. Now, when we get down into part C, this is where we get into the conditional probabilities. Letter C says, given that the sum is 7, find the probability that one of the dice is a 4. Here's a conditional probability. Conditional probability changes the sample space. So I don't want this to be out of that overall sample space of 36 anymore. Instead, I'm going to make this, well here, let's do this without the equation. Let's just go with our chart, right? Given that the sum is 7, so instead of these 36 outcomes, I'm just looking at the 6 blue ones. If I want to rephrase this question, given that I pick a blue cell, what's the probability that it is also pink? How many are highlighted both blue and pink? 2. These 2 right here. That is the overlap. They're both blue and pink, so there were 2 of those. Instead of being out of the 36, it was just the probability that it was out of the sum of 7, that it was blue. There were 6 of them. So 2 out of 6, or 1/3. Now, if I wanted to fit this to the equation, remember, conditional probability, A given B, is equal to the probability of A and B divided by the probability of this condition, whatever follows the vertical bar, the probability of B. In this case, let's start with that. That condition was this, given that the sum is 7. We already said that the probability of a sum of 7 is 6 out of 36. That's going down here in the denominator. This numerator, both A and B happening, well, there were 2 ways that that could happen out of this full field of 36 pairs. 2 ways that it's both blue and pink out of the 36 combinations. 2 36ths out of 6 36. These divide out as they always will. 2 6ths or 1/3. Any questions? All right, letter D reverses the conditions. Now, it's given that at least one of the dice is a 4, find the probability the sum is 7. Or instead, given that we have a pink block, what is the probability that it's also blue? Well, we're looking at how many blocks are pink. Okay? We already have this. It was an A, letter A. There were 11 of them. We had 11 pink blocks. Of those 11 pink blocks, how many are also blue? It doesn't matter if it's blue and pink or pink and blue. It's those same 2. Numerator does not change with conditional probability if you reverse the conditions. Because conditional probability changes the sample space, the denominator. If you were to fit this with the equation, okay, and switch this probability of B given A, this remains untouched. It's just the denominator that's now probability of A, and the probability of A was 11/36. We still got 2 overlaps up there, 2/36. Divide out, there's your answer, 2/11. All right. Now, a lot of this stuff with the equation here, I admit, it's overkill. You took the time to look and analyze at this chart. You don't need to be showing both. But I want to show you why that equation works. Okay? I'm fine with you just using the chart, if you know what you're doing, and you're not just kind of arbitrarily hunting and pecking around. Now, letter E. We're given 2 questions. Are rolling 2 dice with at least one of them a 4 and the sum being a 7, are they disjoint? Are they disjoint? Disjoint means they do not overlap each other. The whole premise of C and D was looking at the overlap. And they overlap here and here. So are they disjoint? No, they're not disjoint. they overlap on 2 cells. Not this true. Letter B. Are they independent of each other? Now again, that question of independence. If they are independent, the verbal definition says the outcome of one has no impact on the outcome of the other. But we need to show that if it's independent, it satisfies this equation, probability of A times probability of B. It needs to be equal to the probability of both A and B. And we test that with a little question mark on top of the equal sign. If they are independent, this will be true. So let's test it. Right? Probability of A was 11/36. Probability of B was 6/36 or 1/6. I'm going to go with a reduced fraction on here because, one, we don't need to worry about adding in a common denominator. You don't need a common denominator for multiplication. And by reducing, it helps keep the numbers a little smaller. Now, this answer, the probability of A and B, we already know what that is. Okay, there were 2 spaces that satisfied both out of the full 36. So if this is true, this should be equal to 2 out of 36 or 1/18. Now, I don't care about the fractions and multiplying fractions. Let's look at this as decimals. 11 times 1 is 11. 36 times 6 is 216. So we've got 11 over 216.0509 to 4 decimal places. 2/36 or 1/18. 0.05 repeating. They're very close to each other, but they are not equal to each other. They need to be exactly equal to each other to be independent. So no, these are not independent. They are dependent. And it is a conditional probability. And reversing the condition, that matters. That affects the probability. Any questions here? Let's try another dice problem. I'll work A and B out with us together, and then I want you to try to answer C, D, the conditional probabilities, and answer that question of independence on your own. So in this problem, we have our 2 events, the probability that at least one of the dice is odd. At least one of the dice is odd. Okay, so that would mean our first die is odd, which is this entire row right here. Or our first die is a 3, or our first die is a 5. Or that means our second die is a 1, 3, or a 5. Now vertically down here, I already have some cells highlighted, so I don't want to highlight them again. 5, 7, 9, 7, 9, 11. So in fact, the only ones that are unsuccessful outcomes here would be even and even. Right? 2 and 2, 2 and 4, 2 and 6, 4 and 2, 4 and 4, 4 and 6, and then 6 and 2, 6 and 4, 6 and 6. So there were 9 unsuccessful outcomes. Subtract that away from 36, we have 27 successful outcomes out of 36, or 3/4. Questions on where that came from? Our second probability is the probability that the sum is odd. All right, for an odd sum, now we're looking at just these sums, the odd numbers. So I'm just going to be hunting and pecking through here. 3, 5, 7, 3, 5, 7, 5, 7, 9, 5, 7, 9, 7, 9, 11, 7, 9, 11. Get this checkerboard pattern here. Every other number, half of that chart is highlighted pink. So that means half of the chart, 18 out of 36, or 1/2. Try these conditional probabilities. Take a couple minutes. Letter C. Given that at least one of the dice is odd, find the probability that the sum is odd. And letter D. Reverse them. Given that the sum is odd, find the probability that at least one of the dice is odd. And then lastly, are these two events independent? Take a minute, see what you get. Suggestion with these is don't force yourself to use the equation if that's not natural here. Right? We took the time with those colors. If you're comfortable with that, you're familiar with that, use that. Letter C. Given that at least one of the dice is odd. In other words, given that we have a green block, what is the probability that it's also a pink block? Well, we had 27 green blocks. There's our new sample space, because conditional probability changes the sample space. Given that it's green, what's the probability that it's also pink? Well, we had 18 pink ones, and every one of them was sitting on top of a green one. So all 18. 18 out of 27, or 2/3. We wanted to satisfy the equation for this. Let's say that overlap, 18 out of 36, was both green and pink. The condition here, at least one of the dice is odd. Well, that was what we had from part A, 27 out of 36. 36s divide out. There's our 18 out of 27. There's our 2/3. Letter D. Given that the sum is odd, find the probability that at least one of the dice is odd. In other words, given that we have a pink block, find the probability that it's also a green block. What's the answer? We had 18 pink blocks. Of those 18 pink blocks, how many were also green? All 18. Every single one of them. 100% chance. So, to test for independence, are these two events independent? Well, you probably can already see this, but let's see if this satisfies our equation. Probability of A times probability of B is equal to the probability of both of them happening. Probability of A, we had said, was 3/4 times the probability of B was 1/2. That one and that one. If this is true, it'll equal the probability of both of these happening together, which we just said. There were 18 that are shaded both green and pink. Out of the 36 cells, 18 out of 36 reduces to 1/2. Just think about this logically, your mathematical algebraic identities. Is there any way that 3/4 times 1/2 could equal 1/2? No. Are these independent? No. Questions? All right, let's abandon something as boring as dice and look at something more interesting, cookies. We have a problem here where Marcy's mom puts a bunch of cookies into a cookie jar. In this jar, we have 27 chocolate cookies, 32 vanilla cookies. Of the chocolate cookies, 7 of them were generic. Of the vanilla, 10 of them were generic. A cookie is chosen at random. Find the probability of choosing whatever. All right, so like we saw last week, we're going to take the extra time to make a chart. We might be able to answer a couple of these questions without the chart, but in the long run, it's going to pay off to create this chart. So let's look at what our variables are. We have the type of cookie, we have chocolate cookies, and we have vanilla. We also want a total row. Additionally, these cookies are either generic store brand cookies or they're name brand or they're non-generic. We also have a total column. All right, let's reread the problem and substitute in the values that we know. There were 27 chocolate cookies, so 27 total chocolate, 32 vanilla cookies. Of the chocolate cookies, 7 of them were generic. So of these 27 chocolate, 7 were generic. And of the vanilla cookies, 10 of them were generic. So of these 32 vanilla, 10 were generic. So those are the only numbers that we're provided with. But we can easily subtract away and add to get our remaining values. Like total generic, 7 plus 10, we've got 17 generic cookies. Working horizontally, 27 chocolate cookies, 7 of them generic. The remaining 20 must be non-generic. 32 minus 10, we have 22 non-generic vanilla cookies. 42 total non-generic cookies, and then adding across or vertically, we have 59 total cookies, same value that we get if we added horizontally. So, having these numbers in place, we can fly through these questions here. Probably some of them. Probability of randomly selecting a cookie and then having it be a chocolate cookie. Well, there are 27 chocolate out of 59 cookies in the jar. 27 out of 59. Vanilla is 32 out of 59. Chocolate non-generic. This is exactly what I had said earlier today, where the and is implied. And if you wanted to get into the equation, you're looking at multiplication, but they are not independent. They do depend on each other. So rather than overcomplicate things, let's just look at the chart. remember everything fell into one of these four quadrants. We want chocolate, non-generic cookies, of which there are 20 out of 59. Okay. If we didn't make the chart, then we're relying on the equation and making it uglier and messier. All right, letter D. Here's where we see a critical word, or. Chocolate or non-generic. Okay, well, if we were to go with the equation, which I'm not saying you want to do, but let's illustrate what happens. Probability of selecting a chocolate cookie, we already said, was 27 out of 59. Or means add, plus the probability of a non-generic cookie, which is 42 out of 59. 42 plus 27, we're already at 69 out of 59, which we know is impossible because we've counted these chocolate non-generics twice. We need to subtract those 20 away, minus the 20 out of 59. So 27 plus 42 we said was 69. 69 minus 20, we're at 49 out of 59. There's our answer. Now, we have this chart in front of us. We could have used that. A favorable outcome is a chocolate cookie, 7, 20, or a non-generic cookie, 22. I've already highlighted that. I don't want to do it again. 20 plus 22 is 42, plus another 7. There's my 49 out of the overall 59. The only thing I don't want are these 10 generic vanillas. So vanilla generic, 10 out of 59. If I wanted to answer my question here, probability of selecting a vanilla or a generic, well, in this case, the only one I don't want is chocolate non-generic, of which we've already said there are 20. So I'm just going to subtract the 20 away from my sample space of 59. 39 out of 59. I could have used the equation again. I could have gone through and highlighted successes. Let's just think about it, right? The only thing I don't want are these 20. I do want these. So I could have added those to get my 39. Any questions here? All right, let's try one more of these. It says, over a 5-year period of time, 80% of winter days in Philadelphia had an average temperature above freezing. 20% of those days had precipitation. Of the days with an average temperature below freezing, 15% had precipitation. A winter day is chosen at random. Find the probability of choosing a day. Make a chart. Does anybody see the key difference between this problem and what we just did with the cookies? What makes this more challenging? Well, the cookie problems, we eventually knew the total number of cookies in the cookie jar. With this one, we have a percentage, which could make this very complicated because 80% of winter days are above freezing, but 20% of those days, not all of the winter days, this is a conditional probability. Given that it's above freezing, 20% has precipitation. All right, well, there are a couple ways you can look at this. Okay? Looking ahead, what the book wants to do is a tree diagram, which on the surface seems to make sense, right? You may and probably have done a tree diagram somewhere along the way. And if you're talking about flipping 2 coins, it's easy. 50-50. We've already talked about this last week. We have 4 outcomes. Heads, 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 tails, tails, heads, tails, tails. Flip the coin. If I want 2 heads, flip the coin, 50% probability it's heads. Second flip, 50% probability it's heads again. I can just multiply along this branch, 1/2 times 1/2. There's my probability of 1/4. It gets a little bit more complicated when you're looking at non-equivalent probabilities. And really the challenge here is you have to be given pretty much every piece of information along the way. Okay? We'll look at this problem in a second, but look at these uneven branches. Okay, 27%, 45%, 26%, 70, 51, 20. Actually, this was supposed to be a 28 there. The way this problem works out, we can make sense of it. But it's not always that clean. I prefer the chart. Let's take a look at this here. Okay? Let's split this apart like we did with the cookie problem. We have winter days in Philadelphia. They are either above freezing or they are below freezing. And we have total days. And those days, they either have precipitation, rain, snow, sleet, hail, vaporous gas, whatever, or there's no precipitation. And a total column. Okay. Up to right now, this is just like Marcy and her cookie. Let's read through this. The key to one of these percentage problems is treat this out of a hypothetical 100 days. That allows you to kind of work with these percentages fairly easily. And it keeps our answers in the format that we want, a percent of the total days of the winter. So 80% of the winter days had an average temperature above freezing. So 80% of 100 is 80. The remaining 20% of the days were below freezing. Now this is where we need to be careful. 20% of those days, implying these days above freezing, means we don't want 20% of 100, we want 20% of the 80 days above freezing. Now, there's no shame if you want to go to your calculator and do 0.2 times 80, get your answer, that's fine. But the numbers here are friendly enough that we can kind of use our reasoning with 10%, right? To take 10% is pretty easy. We just slide the decimal point. So 10% of 80 would be 8. We want 20%, so we'll double that to 16. 16 of those days would be 20%. The remaining 64 days had no precipitation. Back to the problem. Of the days that were below freezing, 15% had precipitation. So these 20 days, 15% of 20, well, 10% would be 2. Half of 2 would be 1, that's 5%. 10% plus 5% is 15%. 2 plus 1 is 3. The remaining 17 days had no precipitation. And we could add vertically here 19 total days with precipitation. Carry the 1, 81 total days with no precipitation, and that looks good. Going across horizontally, that adds up to 100. Sorry. Computer's dying here. Wouldn't want to miss out seeing all those beautiful avatars. Alright. So, I've been saying before, like with the cookie problem, that we took an extra 60 seconds to make the chart, but making the chart made these questions a lot easier. Well, this might have taken a little bit longer, maybe an extra 30 seconds, but the 90 seconds makes it a lot easier to answer these questions. Yeah? Percentage of the days above freezing, 80% were above freezing. With precipitation, 19%. Yeah? That's the nice thing about this, is that they're already in the language of answering the question. Freezing with precipitation, so below freezing with precipitation, 3% of the days. Here's that word or. Percent of the days freezing or with precipitation. Well, a freezing day, below freezing, or precipitation. Okay. 3 plus 17 is 20. 20 plus 16 gives us 36. 36%, which you can see, the only thing we don't want is those 64% of the days that have no precipitation and they're above freezing. Any questions here? Now, what this is saying is that it's tying it back into that general multiplication rule. Okay? All of this work that we've done today with conditional probability, it all goes back to that very first example problem that we did with like soccer t-shirts, right? I said last week, you have 4 t-shirts, colors, and 2 ink colors. How many total shirts can you make? 4 times 2, 8 shirts. It all is traced back to that idea, except when we're talking with probability, well, you're allowed to multiply probabilities together to get your overall possibility. Now, if the events are independent, it's nice, it's easy. A times B gives you the probability of A and B happening. But if it's not independent, then it is conditional. And that second probability depends on what happened in that first outcome. Rather than refer to them as dependent events, we look at them as conditional probabilities. So let's look at a variation here. We had said that the equation for conditional probability is probability of A given B is equal to the probability of A and B let me reverse these. Let's say B given A. Probability of A and B divided by the probability of the condition, the probability that A happens. Well, if you're looking at this as an equation, we want to solve this algebraically for the probability of A and B. Okay, both of these things happening together. Think of that as being over 1. Cross multiply, probability of A and B equals the probability of A times the probability of B given A. Okay, this is the same equation, just solved for the probability of both of them happening. Look at how this compares to our equation for independent events. Probability of A and B is equal to the probability of A times the probability of B. They are so very close to each other. If they're independent, you can just blindly multiply the two things together, and there's your probability of both happening. But if they're not independent, they are conditional. And whatever that second one is depends on what happened in the first case. The general multiplication rule always applies. And means multiply. And even in those cases when the and wasn't explicit, you're still multiplying. But if it's conditional probability, you have to pause and think about what that second probability is. Let's finish up a little bit with the tree diagrams here. We looked at the coin flip. That's pretty straightforward in that case. If we have a case that's a little bit more complex, okay, tree diagrams can still work. Okay? Personally, I don't really care for them. And I'll be honest about that. I'll show you some other techniques that I think are going to be a little bit more universal because, like, as opposed to that Philadelphia winter problem, where we were only given a couple numbers, we were able to answer everything by filling out the chart. Look at everything that's spoon-fed to you in this problem. And this is looking at adult internet users. Okay, so people who use the internet over the age of 18, 20% of that population is between 18 and 29, 45% is between 30 and 49, and the remaining 28% are over the age of 50. All three of those add up to 100%. Now, the Pew Internet and American Life Project finds that 70% of this youngest age group have visited a video sharing site. There's a conditional probability. 70% of the 27%. Next one, 51% of the middle age group, so 51% of the 45, and lastly, 26% of the 50 or older, the oldest group. So on a tree diagram, it looks like this. We first split them by age, young, middle, old. 27%, 45%, typo right here, this is 28%, not 26. Secondly, we have these conditional percentages that if you're in that youngest group, 70% of them have used the video sharing site, middle age group 51% yes, last age group 26% yes. We could put the no's there if they were relevant to this question. But the question that we're interested in, what percent of all adult internet users visit video sharing sites? Well, we want to follow the branches of this tree diagram. So that would mean that with our first decision, let's go with the young group. 27% chance they're in the young group. 70% of those have visited a video sharing site. So we can multiply 0.27 times 0.7. Or they're in the middle age group. Or means add, we add this on. 45% were in the middle age group, 51% of those answered yes, so multiply those two together. Or they're in this oldest age group. 28% there, 26% chance of them saying yes. Work this all out, you get an overall combined percentage of 49.1%. Now, that worked out nicely for that particular question where we're following the same branches every single time. But look at all this information that was provided for us. Okay? We had 6 numbers given to us as opposed to that Philadelphia winter problem where we had 4. No. 3 numbers. So, any questions here? Like I said, this is the kind of thing that you can't just sit back and watch. Okay? You need to practice this. You have a homework assignment due Wednesday morning, which is conditional probability practice. Number 2, rather than working with cookies, you're working with a used car lot. Okay? And you have foreign-made or American-made cars in different colors. And make a chart, answer the question. We have a dice problem. We have a class of boys and girls, but instead of being juniors and seniors, they're passing and failing. Make a chart, answer the question. We have another class, percentages are involved in sports. Follow along, like the Philadelphia Winters. And lastly, percentages of boys and girls on scholarship and not on scholarship. Okay? Make a chart, answer the question. It's not that bad, but make sure you're taking your time, you're working through, and making sense of the problems. This is due on Wednesday morning before our remote day. I also have an additional assignment due on Thursday morning, which is just the multiple choice from the book for this chapter. And just the multiple choice questions. So those problems are identified on that assignment page. Later this week, we're going to practice some of the open response questions together in groups, and that'll be due next week. Right. Any questions? All right, so you guys have a little bit of time, about 8 minutes, that you can get started on this. Have a good one, guys at home. I'll see you. See you Wednesday.